It's a pleasure to welcome and introduce Andreas Wächter from Northwestern University. I know Andreas a long time. He was a PhD student at Carnegie Mellon. He graduated maybe 20 years ago-ish. And then we immediately recruited him to IBM Research, where I was at the time. In that time, great things, I think, happened for Andreas, for me, for the world of optimization, and hence for IBM. So Andreas won the Broyden Prize, the Wilkinson Prize, the Informed Computing Society Prize. And, you know, people know I have a way of turning things about other people toward myself. Two of my two most highly cited papers are joint with Andreas. Half of my U.S. patents are joint with Andreas. So I have a lot to thank Andreas for. I went to his wedding years ago, and that was a lot of fun. Thank you. And Andreas is going to talk to us about this ARPA-E competition, and he's going to tell us what ARPA stands for, and tell us a bit about this frightening new model for federal funding research.
Okay, yeah. Thanks, John, for the introduction. So yeah, thank you so much for having and for coming in person. So it's really nice to see so many people and talk to them directly. If I had known this, I would have prepared some group assignments, but that's, I think, we're going to manage also without. So okay, so yes, I want to talk about the ARPA-E grid optimization competition. Okay, so this is something that ARPA-E, which is the Advanced Research, Advanced Research Projects Agency for Energy. So they said a few years ago, they said, okay, we want to hold the competition that is about developing some software for the optimization of grid. So that's the national power grid. And I said, we mean business. We're really curious, and this is important to us. We put some money on the table, and I said, okay, you can, or up to $4 million we put out for prize money, and you can win this. And that was a very interesting and unique opportunity because the teams that were participating, they were developing algorithms for an important optimization problem, practical problem. But not only an algorithm, you write a paper, you actually had to make sure it demonstrate it actually works. You have to write software that shows that it works. And then also they independently evaluated how you did, and they also provided you with realistic instances. So that's something you also usually have test sets and so on. They gave you something that was really real. So good optimization to make sure we know what we're actually talking about. What's about the power grid, and in a simplified way. So we see here a network of different things. So we have generators. So these are entities that produce power. So like a power station or a windmill and so on. And then on the other hand, we have consumers, loads, and so on. And of course, you need to transport the power from the producers to the consumers. Okay, and then to actually get it to the houses, then there are some called smaller networks that are called distribution systems that really take it to the houses. This is about the large scale, nationwide transmission system. Okay, which goes, there's high voltages. These are these high things that you're standing around and so on. There was about this. In particular, we are solving the optimal power flow problem. So that's something that's solved every day. This is how basically it's decided who produces how much power, which is about minimizing the costs while satisfying demand, of course. Okay, but you also have to make sure. So that things work when something breaks. Okay, so what can happen is a generator, like a power station, can go offline, or a line breaks, or a transformer explodes, or something like this. So because the power grid cannot store anything, you always have to have a balance between what you produce and what is taken out of the network. Otherwise, the whole thing falls apart. You have to take some immediate action. So you have to restore the balance, and also, of course, you have to make sure once you have the power going in a different ways, that you still maintain safety constraints. In the competition, we worked with so-called N-1 contingencies. So these are contingencies, things where things go wrong, where one of the many components fails. Okay. Okay. So the organizer was this agency with a cryptical name, and here is. Okay. So they said what's important to us. We are interested in this because this is what we consider the most pressing problems in power systems. They said we want to have a fair comparison of things that are actually industrially relevant. So things should actually work in practice, and large-scale powered models. And they said it's about modernizing the grid software, and it's organized in multiple challenges. Okay, so the first challenge that I'm going to describe is the one we were participating in. It solved this AC security constraint optimization problem. So this is what you saw before. Things should still work. I optimally want to distribute power, but in a way that if one thing breaks, it still works. This AC is important. AC stands for acute alternating current, right? Which is something that changes over time. Voltage changes over time, and that's a nonlinear physical process. But in practice, this is currently approximated by linear functions, and they call this the DC version. The DC version is what is used in practice every day. So this is how it's decided how much power is produced. But according to ARPA-E, they say that if we have some enhanced algorithm for this, we can save a lot of money. Maybe 5 to 10% in reductions, which, because we're talking about huge sums, might translate into savings on 6 to 19 billions. And also would help to make the system more reliable, particularly now that things are more dynamic. You have on the consumer side, intelligent consumers or people that produce power injected in the network because they have solar systems, or because wind turbines sometimes have wind and sometimes they don't. So, I think something is missed. No, it's not. So I'm going to talk to you about how this was set up, so how it was run, what was expected from us, then what is the mathematical formulation, then show a few solution approaches, how people actually tackled the problem. Then if I have time, also talk about how we did this. And also, if you have questions, feel free to interrupt me now. So I'll stop quickly if there's any question. I haven't really said too much yet. Okay. So how was this done? So anybody could participate, but only people in the US could actually win any of the money. But people also from outside the US were actually teams that participated and did something. So some of the teams received funding to participate. So before the whole thing started, ARPA-E said, hey, do you want money from us? Write a proposal. And then, said, okay, we want to, and they gave us some money so that we can actually do this. What you produced was software, so computer code that they evaluated on instances that you hadn't seen before. Okay, so as I said, I'm going to talk about challenge one, time-wise, a bit time ago. So it started November 2018, and then we had 1 year, and then November 2019, we had to submit the final code. There were some trial events in the middle where we could try out how does it work, how we're doing in comparison with others, and where they could figure out if their platform for evaluating things is working because it wasn't at the beginning. Okay. Here's how the price structure looked like. And I thought that was very, very clever. So for each instance, they told us you need to solve them in 2 ways. So for one thing, you have 10 minutes to solve this, only 10 minutes to solve these huge problems. That's like real time. And then offline, where we give you some more time, so 45 minutes. Okay, so you solve a problem, like one way, and then you solve it the other way. And then we measure you in 2 different ways, like the lowest cost, and then they had some funky performance profiles, and they said if you're within the top 10 for one instance, so if you're in the top 10 overall, then you would win $100,000. So you could win up to $400,000. And the interesting thing is, all the top 10 got the same, and that was pretty clever, I think, because they wanted to attract people that have not worked in this area before. I have not worked in this area before. If they had said, well, the top 3 get something, first one a lot, third one maybe a little bit, the people who have been doing this for a living, why would we even try? So this way, we thought, well, top 10, yeah, we should be able to do this. So yeah, and I think that also attracted a lot of other people. When you won, people like us who got money before, we just received follow-up money for follow-up work. People that did not get seed money, they just could take it home. And I have a friend who did this, who bought a house and who was participating in the other challenges, and he's doing really well, and he deserves it. 26 teams participated. Here's the ranking of the teams. We were number 2, and I think we were pretty proud of that. The first team deservedly made the first place, so that did really interesting stuff. Okay, so this is how the benchmarks looked like. So finally, in the end, we had 17 synthetic problems. The national power grid is not open for security reasons, right? So they had actually a project before this, the Grid Data project, which was about generating realistic instances which really look like how the real thing looks like, but isn't real. Okay, so they had 17 of those instances. They ranged in size from 500 to 30,000 buses. These are the nodes in the network, up to 22,000 contingencies. That's a lot. And then in the end, out of these 17, there were 20 different scenarios, different configurations, different loads, and so on that you had to solve. And there were also 3 proprietary industrial instances. And of course, we got some test sets when we were developing this and could try them out. So computing wise, so I think the idea was let's give everybody that computing power that maybe an independent system operator would actually also use. They said, okay, you have 6 Linux nodes with 24 cores, so parallel stuff. You can use MPI, message passing interface. I forgot, yeah, MPI for the inter-node communication. You can do whatever you want within a node. And it was hosted at PNNL. So in their supercomputer, they then allocated 6 nodes if you were running something. People could use a lot of software. Could use Julia, Python, MATLAB, AMPL. Most people either wrote C or C++ code, or compiled their own code and sent it as Linux binaries. For solvers, well, you have to solve optimization problems, so you use software that's already available. Cplex, Rovi for linear problems, IPOP, Nitro for nonlinear ones. And when you wanted to submit something, there was a web interface. You just said, okay, so here I'm giving you my code now. I want you to solve this instance, run, and then a while back, you then get the result to see, well, does it even run? How's it doing, etc. Yes.
Did you package them inside the code, or did you assume that they have it available?
How did we do this? I think we just packaged that in there. So in our executable it was linked in, but they had licenses lying around. So yeah.
But like Nitro is an example, it doesn't have academic licenses. So if somebody wants to develop something with Nitro giving everybody a free license? Or did you try?
We didn't use Nitro.
No,
I mean, the people that developed Nitro were using Nitro.
Yeah,
I don't know if anybody else used Nitro. I don't think so. But yeah, the interesting.
It's not exactly a level playing field.
Yeah, and yeah, okay. So there were some subtle things where they actually wanted to be more generous than they actually could be, because then there might have been a conflict of interest. So it was a weird situation, but I forgot the details. But yeah, so licenses somehow there was enough there for you to use. Okay, so how does the problem look like? I'm not going to go into a lot of detail, but basically what the power grid is, the way you can think about it is you have these nodes, these buses, and they're connected with power lines. So these are the arcs. In order to describe the system, what you need to say is, what is the magnitude of the voltage at a particular bus? And then also, now that we have alternating current, this means you have like a sine curve and so on. And you have sine curves that are a little off between 2 nodes. So there's a delay. Okay, so you have phase angles that tell you where on the sine curve you are. And then the difference between this is defined by these phase angles. Okay, so the difference between phase angles would tell you how much power would flow. So these are the formulas that tell you how the power flows, how much flows. Okay, you see there's something squared, cosine, so all it's nonlinear. And now, so we're talking about the process that's in time, a sine curve. And one way to representing that also is with complex variables. Okay, so what I have here is, in order to describe the system, when people think of this as in complex variables, you have a real and an imaginary part. So you have real power, imaginary power. Try to sell imaginary power, it's not going to work. So they called this now reactive and reactive power. So in order to describe the system, you needed to keep track for the AC current case of active and reactive power. So that would describe the system.
These variables are they for a particular instant in time?
So those are the variables. No, so good question. So we are talking about a static state system. So the current is changing over time, but it's a sine curve. So it's periodic. It's repeating itself all the time. So the difference between the phase angles is always the same. Okay, so this is a system that's not changing over time. But the sine curves do, but otherwise we're looking for a steady state solution. Thanks. Yeah. Okay, so in principle, if you just say what's the voltage magnitude and the phase angle differences, you can compute how much power goes through these lines. Okay, and then also, of course, you need to make sure that what goes into a bus comes out. okay, into the, so what you have to consider what's happening from the outside of the system. You have power going in at buses that have generators, and then you have also power going out at buses that have the load, okay? And that, have to make sure that also matches what goes into the node from the power lines and what's leaving the node. So that's just a simple linear equation here. So, and I'm simplifying this now, but in principle, if you specify how much power the generators produce, then you have the system described. Okay, that's the thing that you can choose, and then from this follows how the system is running. If you know what a slack bus is, you know why I'm lying.
So I don't know why you're lying, but is it clear there's a unique solution?
So okay, so there's a unique physically meaningful solution, and that's usually the one given the starting points that we have that you go to. There are pathological cases where things can go wrong, but because you also just want to I mean, if you design a system, the physical system can also have weird solutions, and you don't want to have them go to the weird ones. They're just operating in the range where things are reasonable. So for that purpose, right now, I want to assume that the system is then uniquely determined. Okay, so I told you just now that we can play with the power generation. There's one more knob we can twist, and that has to do with so-called shunts. I don't know exactly what they are physically, but they are at buses. And with this, you can also still manipulate a little bit, what happens to the reactive power and active powers. And we could choose this constant here. And for us, mathematically, it just means there's another constant we could fiddle with. Okay, so these are our degrees of freedom. So here's this whole problem. I'm going to say this again. The first four are the equations we've seen before. This constraint is saying that through a line from bus I to bus J, power line, this is the amount of power that goes through it, and that cannot be above a certain threshold. So you want to make sure that, because if too much power goes through a power line, it heats up, starts to sag, and if it hits the ground, you can imagine what happens, right? So this is a safety constraint. And also we need to make sure that everything is operated within operational tolerances, right? It's a minimum maximum power a generator can produce. And also we need to make sure that the voltage magnitudes at the buses are between, this is also a safety concern, between ranges. Okay, so you cannot have, if you have too much power voltage at a bus, that's, it's not good. So it's also a safety thing. These are large non-convex continuous optimization problems, but standard solvers can solve them. Even with more than 100,000 buses, I mean, it's a problem with several million variables, but they can solve this in a few minutes. What's also very interesting is, that was surprising first to me, and I guess still puzzling to many people, is that if you run a local solver, meaning one that finds a local minimum, they actually typically find the global minimum. So I didn't know that. How do I know that? Okay, you can, with SDP relaxations and so on, and bounds tightening, you can compute a lower bound. And whatever people have tried with the instances that they were able to look at, you never could find. So, IPOPT or whatever solver, whatever solution they found, it was never far away from the lower bound. So it looks like that. I mean, there are instances where you don't go to the global minimum, but run a pretty good, like almost global minimum, or maybe even the same objective but different point. But my point here is to say that this is a non-convex problem, so you might end up with different local solutions, but because of this funny property, that's one of the things we didn't have to worry about. So we could just work with local linear solvers. And I'm making I'm making a lot of simplifications here.
Is the starting point for local solvers to have a starting point? Is it ever in play? Like you were saying, if it's a reasonable starting point, you get physically reasonable solution. That's
a good question. So there are standard starting points that, for example, say, voltage is at a nominal place. Lines have a particular thing, generators may be produced in the middle or something like this, and then you can have a starting point. That's not feasible, but this is a starting point. Also, the organizers gave us a starting point that said, from a different configuration for here, this is how the system was running, but it wasn't even feasible. And it turned out when we were trying which one to use, the one that's like the default one with like everything set to 1 or 0, so that worked actually pretty well. Did I answer your question? So this is also typically how people then initialize that, who solve these AC problems. Okay, I think that's it. Now, I want to talk about this problem now, but a little more on a higher level. So here we see this again. The cost function for the competition was a piecewise linear function. Then we see here just the whole 4 lines of the power flow equations. Okay, they were dependent on the generator, controllable shunts. Okay, and if you fix this, you fix these two, these equations would basically give you the state. Okay, so these are the constraints there. These are the line rating constraints to make sure, you know, not too much power goes through a line, and then we have the box constraint. So now for this is how I want to look at this problem now. So I have as degrees of freedom, green, red and blue, green, red and green, and blue is are the state variables. Okay. So if things go wrong, we have to do something, right? As I said before, let's say a generator fails. Suddenly, you know, there's more demand than we actually have in generation. We need to do something because otherwise the system is not operating. And we also have to, of course, make sure that everything with a new power flow is still feasible for the safety constraints. So this is how they asked us to. So the organizers of the competition had a very precise formulation so that there was no doubt what the optimization problem is because everybody had to solve it. So it was totally clear. And they told us what is the recourse action that happens if there's a contingency. And they said, okay, if you look at the active power that a generator is producing, let's say we have like generator I and generator J are right now in the nominal case where everything is fine, producing that much. And now there's a generator that fails and suddenly you need more power. And then the model is that, and that's close to what happens in practice, is that now everybody starts producing more power according to proportionality constant. So everybody chips in more power until you have balance restored again. Okay, so that's a very simple recourse law. Okay, but that's what they told us it is. That's also often how it is modeled in practice. And yeah, this is all here. And it turns out if I specify what the nominal power generation is and I have a contingency, then what happens in the second stage is uniquely determined. Okay. So what I'm saying is, if something goes wrong, okay, the equations already, the way that they go, that they tell us, already tells you now what happened. How does the system look like when something goes wrong? How am I doing with time? I think now I'm losing all the time that I'm trying to save. Let me just skip that for now. Well, let me just very quickly say on a high level, there was also the reactive power, and also the operators also had to figure out what they do with respect to that. And every operator was required to basically maintain the voltage magnitude at the bus they're connected to. And they can do this by changing how much reactive power they produce. But you can only do this within a limit. So if you're trying to compensate for voltage wanting to come down by increasing the reactive power output, but at some point you hit your limit of what you can produce, and then you're allowed to have the voltage drop. Okay, so it basically, mathematically, you have this constraint between the voltage and the Q variables, and that can be written as a complementarity constraint if you know what that is. Okay, but the thing is that this is a complicated, it's a nonlinear constraint, but it's kind of non-smooth. So everything else I told you before is formulas, it's differentiable, and so on. You can use standard mechanisms. This makes it harder. So that was a complication that was also thrown into the mix. Okay. Okay, so now that was so now let's look at the whole thing put together. So this is the original problem. So that is what, if nothing happens, scenario 0, everything is fine. That's what you have. So you want to figure out what is the minimum cost power generation for the base case, but in a way so that if something goes wrong, now you have 500 or 20,000 contingencies. So for which now, okay, so if I specify here what the power generation is, okay, then the system will take a certain state. I can maybe wiggle around with these shunt variables. So what I have here, in addition to, so once I have the power generation for the base case fixed, that's basically now deciding what happens in the second stage, but except that I can tune with these variables a little bit. Okay, but it's not much I can do. But what I'm trying to do is I want to figure out what do I do in the base case? What's the power generation in the base case? So that's the cheapest. But then if I look at contingencies, they will all be feasible. So the recourse action will make sure that no constraints are violated. Okay. Well, that's of course not always possible. There are contingencies that just cannot be handled that way. And also we are solving these problems, and for these large things, you cannot expect us to make things that are, give you solutions that are feasible. Okay, so the organizers of the competition said, okay, fine, you're allowed to violate the constraints. For example, if I look at this inequality constraint here, that's supposed to be less or equal to 0. Okay. They say, okay, you can violate it. I'm giving you a variable that you can increase if you have to, but you pay a price. And the objective function, there's a, under the red stop share button, there's a row. Okay, meaning there's a big constant before here. So if I start violating this by increasing the slack variable t, I pay a price for it. But at least now there is no infeasibility anymore, right? This problem is always feasible. Okay, so basically whatever we give them, they can evaluate and make a number out of it with this thing. Okay, and so because this was a lot of money, there had to be clear that if they evaluated us, that there's just clear what the score really is. So there was a long 78 document that described what actually formulation is. Yeah.
So they designate the formulation. We are not allowed to reformulate anything.
No. Well, no. Well, so this is the formulation. They're equivalent representations. So what I show you here, the formula with the sines and cosines, that's one way of writing this down. But I also told you there's a way of looking at in terms of complex variables. You can also do that. It's basically like a nonlinear coordinate change. Okay. So you can also write this. Then you have quadratic constraints. Okay, not this sine stuff. So that was okay, as long as in the end you give them something that fits into this thing. So you could, you can do random stuff, okay, and do anything, and then, but eventually you got evaluated with this. So the rectangular formulation is an equivalent formulation. Okay. So now this is what happened if you were given one instance. So when they said solve this is what's going to happen. They said, okay, here's a phase one, and you either have 10 or 45 minutes, whether they pretend we are the real case or the offline case. Okay, do whatever you can, and you now will have to commit of what happens in the base case. So you have to decide how much power do you generate in the base case, or you set your chance, and also tell them, look, if I do this, this is how I tell you the system looks like. So I have to commit after 10 minutes to that. Okay, but then, for large problems, you cannot even have looked at all the contingencies. So then they said in the second phase, now you have to tell us, okay, so given that you have decided on what the base case generation is, G0, now tell us how you would like to set the chance and how you think the system then looks like. Okay, so we had way more time for this, but at the end then what we had to do is, for each of the contingencies, give you variables for this. So yeah, does that make sense? Yeah, okay. And we had much looser time limit. I can tell you a story with that, but I'm not going to do that now. But so yeah, that's how it worked. And then, so if you in the end gave them now what all the variables and colors and so on, if you gave it to them, then they said, okay, now I can compute what the cost function is. There's a formula for this. And now I can also measure by how much you violated the constraints. And then the formula there tells you that's your score for that particular instance. Okay. Those are box constraints, like power generation cannot be below the limit. Those were hard constraints. If you violated those, you got a huge penalty. So basically, you really shouldn't do that. But it's hard, it's easy. You can just project them, right? Yeah, you would. Yeah. Okay. Okay. So different solution approaches.
So what was rho? You know what rho was?
Yeah, so yes, so all constants here were given. Rho was so it's a penalty term that tells you by how much you pay for constraint violation. And it was actually a 3-part piecewise linear function, which at the beginning you didn't get so much penalty, but once you started hitting a certain penalty, constraint violation, you get really penalized. So it was a good incentive not to do that. Okay, but if a little bit of constraint violation wasn't that target. Okay, so I'm going to show you now how some of the teams in the top 10 solved this. Okay, and but before I do this, I should tell you again why it's so hard. But these are large problems with up to 30,000 buses. If you just have to solve an optimal power for problem of that size, that's not so hard. But now with up to 22,000 contingencies, that's huge. If you would just naively write it down, you would have a 14 billion variable problem. Of course, you can't solve it like that. Okay. In addition, we had a pretty tight time limit. 10 minutes is not very much. 45 minutes, it's not really much for that kind of problem, right? So if you wanted, and it was a difficult problem, so it's non-linear. Right? We had these weird complementarity constraints, which have somewhat of a non-smooth or discrete structure. And also these problems are ill-conditioned and degenerate. So just numerically, they're somewhat challenging. So how do you solve the problems? You know upfront that you can't solve them, so you simply do the best you can. Okay, and then find whatever solution you can come up with. It is, of course, critical then that you use whatever you know about the structure. I mean, there's an obvious structure that you see and that we're going to discuss, right? Domain knowledge. So we had a power system expert, Dan Molzer, on our team, and we wouldn't have, I mean, he was the one who had all the physical insights and so on that helped us to do stuff. And extremely crucial, of course, because you had to give them the software that you write robust software, doesn't have a bug, that is running efficiently and so on. So that was a huge part of the whole thing. And then because these problems are so hard, you needed to make use of all these, they had six computers, each having the different cores. You need to make sure that you're using that. And then you have to forget that you're an academic and simply have the clever tricks to figure out how you're actually solving this problem. I mean, that was so when we started this and we wrote a proposal, hey, we want to solve the problem, and we have this great idea, actor set methods, decomposition, blah, blah. And we believed it, and then we got the money, and then you're faced with reality of a year. Oh, software has to be written, and this great idea we had isn't working at all. And to make it work, we would have to have a lot more time. So in the end, this great idea, boiled down to just having an algorithm that is working. And well enough so that we placed second. But so that's the thing. There's not really a paper that we could have written about a nice theoretical algorithm and so on. All right, so of course, you've seen the structure. I already wrote it like this. There's a base case, and there are these contingency cases, okay? And the only thing that is coupling them is the red variable there. So once I fix what the red variable is, I now have another optimization problem, and actually k many, that I can solve independently. Okay, it's a two-stage optimization problem structure. So I can now say, okay, if I decide what the base case generation is, let me just solve all these problems in parallel. And I will say we're evaluating these contingencies. So this is in parallel. That's where we can use parallel computation. Okay. Here's an important observation in practice. And Dan, our expert, already told us that that would be the case. And yes, it is the case. So if you pretend at the beginning that you have no contingencies and just solve the original problem, turns out that most of the contingencies are actually feasible. So, I mean, that's kind of by design, right? You want to have a robust power network. So if something goes wrong, it should work without even too much effort, right? So most of the contingencies actually have them a zero constraint violation if I do some action, okay? So I can make them work well. And I wouldn't have to change the base case generation. Okay, but there are a few contingencies that really become infeasible. So that means you now have to change, you have to really take into account some of the contingencies that cause the problem. Okay, so in most cases, yeah, I just said that. So because there are just a few of those critical contingencies, most teams said, okay, there's no point in looking at all the 22,000. Let's just try to figure out what are the important ones and then solve a problem restricted to those. Yeah.
So in the data that you were given and in the data that it was extensively tested on, is like the network structure known or almost known, and just the demands and loads what you need is what changing from instance to instance? So like, can you look at the network and just based on the topology say, okay, these are the things that I should be watching out for?
That's a very good question. So we were given test problems, right? And we were given test problems with a certain structure, okay? They had names according to how many buses they had. And that was the same structure. I mean, then you would maybe have a line would not be there or the generator might be off, but there was the same network. And then when we actually saw unseen data, we would see some of those instances. And, if we knew what are typically the tough contingencies, we could exploit that. And we tried to. But then part of their competition is to say, we're also giving you a brand new network you haven't seen before. Okay, I mean, how real is that? Right, so if you're having a network, you would never try, you would have to go to Mars, where there's nothing there. Somebody builds a new network and you suddenly without nothing would have to solve this, right? So that wasn't very realistic, but yeah. So they asked us, yeah, okay, I'm giving you totally new networks and do this, right? But yeah, so we tried this. So for the networks that we had seen before, we kind of figured out what are typically the hard contingencies, and those are the ones we tested first. But yeah.
Okay, on the last bullet, so when you solve this just with the critical contingencies, you then sort of get into a loop where you all of a sudden now some of the contingencies that didn't look critical now became critical because you picked a bad base.
Yeah. So I mean, the different teams are different in different ways. So just to tell you now what we did, yeah, we basically started with some set of critical contingencies, tried to figure out which are contingencies that are now infeasible, added them and so on. You can't cycle these because you kept adding.
Oh, you never.
Yeah, but well, yeah, we did.
Go out of control with that?
Well,
Doesn't go out of control. It can't
well,
be.
there's a time limit for the big one. Yeah, yeah, no. And yes, it's true. I mean, you know, there's a contingency that worked fine when you tried one power generation setup, but now you're changing it because you want to mediate some of the contingencies and maybe some others won't work anymore. That can happen. Okay. So this is how the team solved the problem that did first, placed first. This is met by Cosmin and Petra at Lawrence Livermore. And what they did, they said, okay, this is a two-stage problem. So I have this, you know, the nominal operation. And then I had this part in the objective function here, which was basically just the constraint violation for the second part. Okay, so this was the problem here. Okay, and the only communication was this phi variable, phi function here. And they said, okay, well, I mean, just to evaluate the function, really, I would have to solve an optimization problem. That's why these problems are so hard. And they said, well, let's just replace this function and approximate it just with a convex function. Okay, sorry, I had, yeah. So they said, okay, let's just approximate this. Now we have an optimization problem just in these variables from the original problem. Okay, and you know, let's solve the problem and then maybe update our approximation. Okay. And so that's what they did. They said, okay, let's try this out. We have some approximation. Let's solve the problem. And then they say, well, our approximation isn't good anymore. Let's fix our approximation and so on. Am I making sense? Yeah. Okay. Okay. So the key now is what approximation did they use? And that is clever and surprisingly easy, and it's amazing it worked so well. They simply said we mimic what the system operator would do. So you're operating your system now. There's a contingency that, you know, it's a big generator, and the generator fails, and now your problem is infeasible. What would you do? You would probably say, well, it's a problem. If this generator wouldn't produce anything, it wouldn't be a problem, right? Then if the failure of the generator wouldn't hurt me, wouldn't make a difference. So they say, okay, if there's a contingency which causes a problem because it's a generator that's producing a lot fails, just make this generator produce less, right? So what they said is we introduced a penalty term that is penalizing the fourth order of the constraint of the power output of that generator. Okay, why fourth order? Seems to work well in practice. Okay, so this is now a term that you put there for a contingency where the generator failed and you had a problem. Okay, so by making now this generator produce less, hopefully you better with this contingency. And now what they did is with this factor P there, then now each time when they had in their over loop, each time they optimized this master problem, then they re-evaluated what the true function is and adjusted this function, this parameter here, so that you know, each time they actually have a match. So they show them that, okay, now I have a good approximation of this cubic function here. Like I realized towards the end, I'm not sure how much sense I actually made, but if you followed me, great. But so the basic idea here is just, it's amazingly simple, and it was good enough for them to place first.
This generator fail can be multiple.
Oh yeah, it's n-1. Yeah, yeah. And I mean, it's something similar, of course, when you have a, so with lines, it's a bit similar. And so complementarity constraints is just set, we relax them and then we just project them back. And somehow that was still good enough.
How do you decide PO?
So yeah, sorry, that wasn't so clear. So you're okay. So in the first point, so at the beginning, you're optimizing the base case, then you have a G0. Then you compute what is the constraint violation. So you actually compute you solve the second problem. And now I choose your P so that at your current master problem solution, they match. Okay, so now it is locally a good approximation. Okay, now you work with this approximation, you do this, now you have a different G. So now they don't match anymore, and then you adjust P. So that wasn't so clear. Any question?
So we're talking about this two-stage and management contingency, like, are there differing and actively researched approaches for just dealing with those nonlinear constraints? Did everybody kind of do it the same way?
What constraints?
Just the original nonlinear AC distribution problem. Just that one on the left.
Yeah, so
Is that still a research question?
how to solve them?
Yeah, or is it sort of kind of known and everybody does it?
No, I mean, no, not necessarily. I mean, you have two ways of, we had this. What's that? So one is the rectangular formulation with the complex variables, and the other one is this one. So, it's not clear which one. I mean, they are equivalent, but some are harder to solve than others. But it's not even clear what that is. So people I don't think there's any sense of what the best one is. And it also, of course, depends what solver you're using IP-opt or using something else, so. All right. The next method, I'm not going to say much about this, but this was the third place, was Andy Sun at Georgia Tech, who's now at MIT, I think. Basically, they have an ADMM method, alternating direction of multipliers method, and I'm not going to say now in detail what that is. It just relaxed the constraints, and somehow by relaxing two of them, they had able to have a nice convergence result, that they actually proved convergence of this algorithm, which was new because the ADMM methods usually don't have a convergence result. So they actually proved something. Okay. So then this is a version that was done by, well, I'll show you later. This is the version that's close to what's done in practice. So here, you see this original formulation with the V and so on. But if you linearize this, assuming that the V is around 1 and the angle is small, that actually can be approximated by a linear function. So that's what is the DC approximation. So in practice, instead of having this complicated nonlinear constraint, you actually just have linear constraints. Okay. And that's the DC formulation, as I said, that's solved every day. And also it means that you don't, just in this way, you don't have to deal with these reactive powers. So it becomes a linear problem with fewer variables and so on. And of course, I mean, it's linear two-stage problems. It's clear how to solve this. You can use Bender's decomposition and so on. Now, because they had to solve this nonlinear problem, the AC problem, they couldn't just stop then. They had to have some tricks how then get back values for all the variables so that they were feasible. Okay, so there were some different versions that they did. This was Carrie Baker, 6th place, and then Carlton Coffin, 10th place. And here is a weird one. And I put this here not because it's necessarily the best method to solve it, but just because to show you what kind of broad approach people used. So this was a commercial company in Pittsburgh whose business is to do circuit simulation. So large digital circuits that you have on a computer, okay? And what they did is they said, well, look, actually, if we look at the electrical power grid, that is actually equivalent to some digital circuit, to some power circuit, electrical circuit. You can prove that and so on. So instead of looking at the power grid, you just look at the circuit. And they say, okay, so now this is something we know. We know how to do circuit simulation. They don't really know how to do optimization. So what they did, they just said, okay, let's now actually write down the optimality conditions, which is a nonlinear system of equations. Okay. And that's also a circuit, because I can make a circuit that's a derivative of a transformer. Up there, that's a derivative of a transformer. It's just some weird, electrical thing. And then they said, okay, that's how we solve it now. They use some kind of interior point algorithm, but in a way that nobody would do in practice. Nevertheless, they were able to get 8th place. I mean, yeah. So, but here you can see that this was a nice thing that has really attracted people that usually might not have done this. And if there would be collaboration between these guys and like, I almost said serious, but more experienced non-linear optimization people who knows what would come out of this. Yeah. The way they handle complementarity constraint, that they said, look, a diode looks like that. So that looks a bit like a kink. So let's just approximate it that with a function like that. Okay, so what's the time? Any questions?
Tell us what you do.
I kind of told you already. But what I should tell you is our team. So Frank Curtis at Lehigh, he is a nonlinear optimization person like me. Dan Mozan, he's our power system expert. This guy is amazing. He knows everything I know about power systems. I learned from him. Yeah, okay. So without him, we wouldn't have, okay. So then we have Elizabeth Wong and myself as people who also write optimization software. She's the co-developer of the code SNOpt. Ermin, my colleague at Northwestern, she does a lot with networks, so she was our network expert. And then our joint PhD student, Ruby, was also helping us. So, as I said, the way we would do this is we try to find an initial guess of our critical contingencies. So we would solve this problem only for the critical contingencies, then solve the corresponding problem. No, I mean, this is now a big non-optimization problem where we explicitly keep this. Is that clever? Probably not, but that's the way we did this. And then we tried to figure out, did we miss some contingencies? If we did, then just add them to our critical set and we solve this again. So we had a loop in which we solved this problem, where each time the problem grew. It's not the best thing to do, but it worked well for us. And then it's okay because the number of critical contingencies were not that many. Okay. Yep. Okay. And similar approach was done by Hassan Hijazi. So one thing you of course have to do once you solve this, found some potential solution, base case generation, you now have to figure out, well, what is the constraint violation for all the contingencies I haven't looked at yet, that I haven't included yet, right? So at the same time, where we were solving this large nonlinear optimization problem on one node, we now had still 5 other nodes. And we're in parallel, like crazy, we were evaluating these contingencies to find contingencies that were still infeasible and that needed to be added.
Great. The kind of synchronization of this. So are you working on the next G0 while you're evaluating the previous G0?
Good question. Yeah, I'm going to tell you in a second. It's a very good question. And I'm good. Yeah. So in our approach, let me start at the top, okay? So we need to make sure that this set of critical contingencies is as small as possible because our problem would grow with that. There's some obvious stuff you can do at the beginning. If you have a bus and there are identical generators on it, and one of the identical fails, then another one fails, it's the same contingency mathematically, right? So we did some pre-processing and took that out, or parallel lines, we took that out, okay? Where did I put? Oh, that's actually a different slide. Okay, so where was I here? So I told you already, this is what we were doing. And we would evaluate this in parallel. So what we did, while we were solving the master problem, we were going through all these not yet included contingencies. There were too many to go through each time. So we had a priority list based on, some heuristics, how much power is going through a line. This might be an important contingency and so on. We had this priority list. So while we were evaluating the contingencies, we followed that priority list. So if you didn't get to the bottom, hopefully that wasn't bad. And here it is. So once we actually done with our big master problem, in the meantime, we have been in parallel evaluating contingencies with the previous G, right? With the previous power generation. So it's not the same. So we use then this previous constraint variation as a priority list. And we now went down this list, and before we added something to the master problem, we checked again for the most recent version. Okay, so if you didn't follow that completely, but it's right, there's a mismatch between, yeah, okay. That's the slide already did. So yeah, so we moved redundant contingencies at the beginning. And then here's another thing that can happen. You might have contingencies that are kind of related to each other. So if you took care of one contingency, maybe it automatically actually helped to take care of another one, maybe because the lines are closer to each other, or like generators are similar in a similar place in the network or so. Okay, and you want to avoid that. You want to avoid that you add now two contingencies and making our problem bigger if it was enough to just add one. And our student Ruby came up with a very simple heuristic that said, okay, if you evaluate a contingency and figure out, is this a feasible one or not? Okay, then you look at which of the constraints is the one that is the most violated one. So maybe it's this line that's, there's too much power going through this line. And then we looked at all the contingencies. So we were adding a contingency, and there was another contingency. We checked, is the constraint that's most violated the same one? Then this is dominated. We didn't have to look at the other one. So that was our heuristic, and we kept doing this. So now we're getting really more into the details that maybe not everybody wants to follow. But so that's what we did here. Yeah, I'll tell you that. So when I talk about evaluating a contingency, this is the optimization problem we had to solve. We wanted to find variables B and X so that the constraint violation is minimized. We wanted to find a feasible point, and by minimizing the infeasibility when the objective function was 0, that's good. Otherwise, we would at least find something that's least infeasible. That's an optimization problem. So if you talk about the iterations that an optimizer takes, it's like 50, 60 iterations to solve this. Okay, but what you could also do is to say, look, remember, these are the power flow equations. Okay, so this is just a nonlinear system of equations. And I could say, okay, so let's just fix everything as it is in the base case. I'm not even messing with these shunts, and compute what is the state of the system, the state variables, right? And I told you in many cases, the system is already doing well. I don't have to do anything. So instead of solving this big optimization problem, let's just solve a nonlinear system of equations and see what happens to our state then. Maybe what I get here is already feasible, and turns out, yeah, that's actually the case. So often when we are going through these contingencies, then we would just do this fast contingency evaluation by just basically solving nonlinear system of equations in like 5 iterations instead of solving this problem with like 6 iterations. That was an incredible speed up for us. So here you can see now that I'm now talking about heuristics that you would not put into a paper necessarily, not a math paper with proofs. Okay, but these are the little tricks that actually helped us to actually solve these problems. And so if it turned out it was not feasible, then we actually did solve the full problem. So here I show you kind of how much. So these are these are different networks, different with different sizes. And what I'm showing you here is what fraction of the entire contingencies could be solved in this quick way. You can see for the large problems, almost 80% of the contingencies could actually be solved just in this fast way. So you can see, you can get quite some speed up here. And here's how I also, this is now where I show you computation time. Okay, so we were able to solve up to like almost 50% of the time by doing this fast evaluation. Okay. We wrote stuff in C++, a lot of code. We used IPOpt to solve this as an open source and point solver. We used MPI. We wrote our own like parallelization scheme and so on. And so all these were the technical things to make it work. And here's some more tricks that we had to do. These are the dirty tricks. So when IPOpt fails, okay, just use the best iterate you had instead of just failing, or take the last iterate. That's usually what you would do if you would use a linear solver. So that's one of the dirty tricks. We just kept each iterate and measured which is the best one, and then just kept the best one and returned this. And yeah, because I'm running out of time, I'm not doing this. Going out through all the details. But so that was challenge 1. Challenge 2 was like, I guess last year. That was more complicated in the sense that now you could actually have these 3 decisions. You could decide, do I switch a generator on or off? Do I have a line on or off? Okay, so this becomes now more complicated because now you have discrete decisions to make, right? On the other hand, they now had a very flexible recourse. I told you about this thing where you had this proportionality constant, right? So there's a very specific way you can react. Here, you could do whatever you wanted. And as a consequence of this, because you have so much freedom, the contingencies didn't even matter. There was a totally unintended thing, but you were doing well when you solved the first problem well. Okay, at least, I mean, if you wanted to get a little bit out of this, then you had to do a little bit more work. Okay, but that was, so that was weird. So we put, I was trying to think.
These different actions make cost different, right? It was more like a feasibility check before, but now they introduce any cost function to it.
Yeah, so true. So there also then was a much more complicated objective function where you were allowed to shed load and so on. Yes, but it still was weird. So because you had to just solve the base case. There's now a new challenge, which is our multi-period, so over time, where you have whatever. So we participated somewhat here. We didn't have that much time anymore. We placed 7th. Yeah, okay. And so just to summarize, it was fun. So it was a great thing to do, but you don't have that opportunity. So you have real instances that somebody tells you that's important, and that you also have to prove that it's not just a theory paper where I have some trial experiments and so on. I'm giving you actual software that runs well. You know, many different approaches. We have a paper where we describe how we did this. Oh, one thing I do want to say. So I was a bit disappointed when we were done and we were talking to independent system operators. They didn't really care. Okay, I was like, okay, I thought we have this important problem and hey, look, we did this. Okay, no, not really. But I think the intention here was to basically break a myth. In practice right now, people work only with this linear formulation. Okay, and everybody tells you the other one is way too hard, you can do this. So this was a proof of concept that no, I mean, nonlinear optimization stuff that people like we do is something real. You can use it in practice. Okay, it's difficult and we're not there yet, but I think that was the intention of ARPA-E here. Okay, so I guess I rushed through the last part and I'm over with 1 minute. So, but thank you very much for listening and yeah.
I was wondering why the ISOs do not care about knowing, like, is there market consideration or they care about tractability?
I mean, I don't think that they don't care. I mean, they have to, I mean, of course, they need AC feasible solutions, right?
Right.
So they do this. It's just that these approaches that we have immediately, they're not really interested in that. I mean, one problem is just you want to keep the lights on. So robustness is way more important than making things cheaper, right? And yeah, so I think that's, but if anybody, so I should say now, I'm not an expert in power systems. What I tell you here is what I gathered by osmosis through Daniel and, but I hope the statements I'm making are kind of right, yeah.
Well, so you started on your introductory slide where you were quoting the sort of setup, that the premise was that if you actually do AC instead of DC,
Yeah.
hopefully you'll save 5-10%.
Yeah.
So did this carry through this hypothesis?
So we didn't, you mean in terms of what that actually meant in actual dollars?
Yeah.
So there was no, I mean, when they said enhanced algorithm, it's not only this. I mean, there's also the other phases and so on, all the other things taken into account. So that's a study where I guess if you do many things, including AC formulations and so on, you get there. I mean, there was no attempt to figure out what the actual projection would be. Does that make sense?
Any other questions?
Is your code publicly available?
No. For two, the main reason is it's messy. I mean, I would be a little ashamed to put it out. And also it is so specific. I don't think there's anything that you would do. And then of course, I mean, if it turns out that there's some interest, so maybe we can, that was the hope, maybe commercialize it somewhat, but of course that's insane because it was just too much work. And there was no interest.
Does ARPA keep the code?
No, they don't have the code. No. But I mean, they really they're trying to, that's their mission. So they're trying to do this. And that's how they fund things. So they want you to then collaborate with someone, but that's just not realistic for people. The kind of research we do doesn't give you that really. You have to do that in some other way.
Can you use the instances for your future research, like instances that were?
Yeah, so everybody, if you want to, they're all available. Yeah, and I mean, if you care about power systems, these are good test sets, so they're very helpful.
Any other questions?
There was one, yeah.
You talk about the heuristic of the most violating constraint, and does that has anything to do with the topology of the network? Maybe some isolated node. If that fails, it will cause a lot of damage to the other parts.
Yeah, so it definitely has to do with the topology. So so the thing from what I mean, nonlinear power flow is a little strange. So something can change in one part of the network, but the effect might change something remote, at least in some cases. So I cannot explain to you now what actually the network correlation would be. And we tried a lot of stuff. We tried, different heuristics and so on. It was the case that this simple heuristic was enough to figure out when a contingency seemed to dominate another one. So, and this is the thing, we had a year, that question came up late. You don't have like 2 months to now try out all these things, make some scientific insights. You just, works, let's move on. So that was a taste of like real world, yeah. Okay.
Great. Thanks again.
Okay, yeah, thank you for coming.